Good morning, all. Welcome back to electricity, to current electricity. I'm going to spend some time today looking at 16.7. I want to take a little bit of the homework up from 16.6, looking at series and parallel circuits, and then we're going to use that to launch into our complex circuits today. So just quickly to put things in perspective, you can see here we are the 16th, so I'm not going to post a video note. This live stream video will be our note for 16.7. I'm going to finish chapter 16 tomorrow, and then 3 more notes and we're done. I'm going to do the live class. I've got a live class booked for the 18th. I might move that one. I probably will leave it on the 18th, or maybe I'll just move the live class to the 22nd to the 23rd. That way we can take up any questions that you have ahead of next Wednesday's test, which is our final day. All right, so let's go back to our book. I'm going to start with some of the questions from here. So question 29 says I've got a string of lights that has 25 bulbs in series, which draws a current of 3.8 amps and from a 120 volt source. So by now, you probably realize that a lot of our voltages are around 120, maybe 117 or 121. But again, that's what your outlets are at home. Right? So when you plug something into an electrical plug, the wires that are coming between the outlet and your device are bringing 100 electrons with 120 volts of potential, and that much energy. So if I look at question 29 here, let's get this chemistry stuff off the whiteboard here. Okay, so I've got 25 lights, I've got 3.8 amps and 120 volts. So again, if I've got a power source, okay, it's my power source, and it's going to feed 1 bulb, 2 bulbs, 3 bulbs, 4 bulbs, etc. Until I've got 25 bulbs, I'll put a little switch in here, right, and there's my circuit. And I'm told that the currents leaving the wall is 3.8 amps. Okay. Now, if each of these bulbs is its own resistor, so there's bulb 1, bulb 2, bulb 3, all the way down to bulb 25. Okay. And I know that the voltage at the source here, so I'm going to call that I0, which is my zero or initial current. And I'm going to give myself a total voltage or an initial voltage, you can call it VT for total voltage, of 120 volts. Then if I actually go through and try and figure out, if I know the current and the voltage, I can calculate the total resistance in the circuit as V equals IR, R equals V over T. So I will get a total resistance. I'm going to work through these. I like to do them as we're working through them. That way you can see how kind of fast it is and easy it is to. Okay, so I'm getting 31.6 ohms or 32 ohms, right? 2 sig digs because of my current up here. Now, if I know that the total resistance for these series bulbs is 32, I know that the total resistance is also equal to R1 plus R2 plus R3. I actually have 25 individual resistances, right? Where these are the resistances for each of the bulbs, right? So if I know that 30, so the Rn, which is the resistance of any one bulb, is going to be RT divided by 25, right? And the resistance of each bulb turns out to be 1.3 ohms. Right, for any one bulb. So I now know the total resistance. The question is saying, calculate the total resistance, calculate the resistance of each light. It says, what is the potential difference across each light? Now I know that electrons come out of here with 120 volts, right? And as they do, they're going to go through the first resistor and they're going to use some of their voltage. They're going to take that 120 and divide it into all these bulbs because they need energy to push their way through each of those bulbs. So if I want to find the individual voltage for any bulb, I'm going to take the current going through the bulb times the resistance of the bulb. I know the current is 3.8 amps, but I also know, according to Kirchhoff, because there are no junctions, the current remains constant. So the current here stays at 3.8 amps times the resistance of 1.3 ohms. Oops, 1.3 ohms. And I should get 3.00 volts. Right, so the voltage at each bulb is 3 volts. The voltage for the resistance for each bulb is there, and the total resistance for the circuit is there. Okay, so those were the A, B, and C answers. I could also have taken, I figure if I've got 25 bulbs sharing 120 volts, I could just take my 120 divided by 25, and I should still get 3 volts. No, that's not going to work out, is it? Current times resistance. $32 ohms. 1.3 ohms. Oh, sorry. I'm getting 4.8 volts down here. Okay. And now if I take my 120 volts and divide it by 25, I'm getting 4.8 volts. Right, so I'm going to divide this by the 25 resistors. Each one is going to draw, take it down. So if I was to measure the voltage across any one bulb, I should get 4.8 volts, right? Which says the difference between the electrons here and here is 4.8 volts. They had 4.8 more, and they've lost it when they get to here. So if they had 120 and they lose 4.8, they'll have 115.2 when they get here. Right? This doesn't tell me the 120 or the 115.2. It tells me the difference of the electrons between this point and this point, which says that they have actually lost 4.8 volts. Okay, so there's question 29 from the homework. If I look at question 30, 30 says, what is the resistance of a coffee maker drawing 5 amps from a 117 volt source? Okay, so let's that's not going to work. Okay, so the voltage is 117 volts, and the current is 5 amps. Okay, and the question is, what is the resistance? Right, V equals IR, every step of the way, over and over and over. So we're going to get our resistance here, 117 divided by 5. 23.4 ohms. Okay. So when electrons leave the wall and go through the coffee maker pushes back on those electrons with that much resistance. Now, so B part of the question says, what resistance would have to be added in parallel with the coffee maker to increase the current to 15 amps? Okay, so if I'm going to increase the current to 15 amps, notice that my voltage doesn't change. I'm using the same plug, but I just want the electrons to go faster through my circuit. Okay, so I'm going to have the same voltage, but now I want to increase my current to 15 amps, which means I need a new resistance. This is an important question because it sets us up for a bunch of the other ones that are going to come up in a minute. Right? This is 7.8 ohms. Okay. Now, what that's saying is that this is my circuit, this is my source, and I put my coffee maker in here. It's going to be drawn as a resistor. Right. And I know that it's a 117 volt source, that I have R1 here, which is, 23.4 ohms. Okay. And my current was 5 amps. Okay. I want to make the current up to 15 amps. So the question says, how much more resistance do I need to add here in parallel to make this work? Now, if I know that my total resistance in the circuit is now going to be 7.8 amps, 7.8 ohms, I've changed my current from 5 amps to 15 amps, right? So it was 5. Now I've added another resistor. Okay, and the current goes up to 15 amps. Okay, so that being said, with 117 and 15, I'm getting a total resistance of 7.8 ohms. But remember, this is my total resistance for the circuit. And I know that 1 over RT equals 1 over R1 plus 1 over R2. I know RT, I know R1. So I'm going to put my numbers in here. I've got 1 over 7.8 equals 1 over 23.4 plus 1 over my unknown new resistor, R2. Now, that being the case, what I'm going to do on my calculator is I'm going to take my numbers, again, let's just rearrange this for a minute. 1 over 7.8 minus 1 over 23.4 equals 1 over R2. So I'm just going to take my 1 over 23.4 and subtract it from this side and subtract it from this side. Okay, so I just moved it from this side of the equal sign to across to the other. So now I'm going to take this number here, 7.8, and hit my 1 over x, minus, I'm going to put 23.4 and do 1 over x, and I'll get an answer. Minus, I'm getting 0.0855. Okay, now to solve for R2, I'm going to bring the R2 up. I'm going to take the 0.0855 down. So I get R2 equals 1 over 0.0855, but I already have the 0.0855 still on my calculator. So I'm just going to say R2 equals 1 over this number. So let's just leave it on there and do 1 over x. I'm getting 11.7 ohms. So what that's saying is if I put an 11.7 ohm resistor here, right, some of the current leaving the source will go through this resistor and some of it will go through this resistor, but in total, I've increased the current by increasing the resistance, by decreasing the resistance. So something should be jumping out at you here, right? I'm saying the first resistor is 23.4 ohms. The second resistor is 11.7 ohms. And when I put the two together, notice I'm getting a total resistance of 7.8 ohms. That's impossible. how can I have less resistance now? I have this much resistance and I've added another resistor, but I've lowered their total resistance. Well, it turns out that electrons that had to go through here had this much resistance, but they only had the one path originally. Now I've actually given them another option, even though the other option is 12 ohms. Because I've given them two possibilities, right, it makes it easier for all the electrons to get through. So I lower the overall resistance of the circuit, right, when I have them in parallel. Okay. That doesn't seem to make cognitive sense mathematically unless you look at what the electrons are actually doing and what they're experiencing as they go through the circuit. Okay, so keep that in mind. When you have two resistors in parallel, 23 and 12, the total resistance is going to be lower than the lowest one. Will always be lower. If this was 100 and this was 1, the total resistance would be less than 1. It would be 0.9 or 0.8 or 0.3 or something. Right? But it would have to be lower than the lowest resistance, because even though whatever the lowest one is, I've already given them another option, and having two options makes it a little bit easier for them in general. And I really wanted to make that point with this question. Right? When you've got two resistors in parallel, the sum of the total resistance resulting from the parallel resistors is lower than the lowest resistance. Okay, so there's 30. Okay, so that's an important lesson as we move forward to start looking at complex circuits today. Let's look at 31. I'll do 31 and 31, 32, 33. So 31 says calculate the total resistance in each case if I have 20, 30, and 60 ohms in series. Okay, so 31, there was 30. So 31 says I've got these three resistors in series. And again, you know that as electrons leave the source, if they have three resistors to go through, it's going to be hard to get through the first one. So here's R1, R2, R3. And as the electrons come through the circuit, they're going to have some resistance here, which was 20, then 30, then 60. So basically, and again, this is really important. If there's 20 and 30 and 60, I'm going to have some resistance, and I'm going to have to push harder to get through the next one. Then I'm going to have to push some more. So I'm having to push each step of the way, which means I'm using voltage at each step of the way to push through. And for resistors in series, remember, I add them up. So 20 and 30 and 60 is 110. So what this looks like to me is if I could squeeze these all into one resistor, right, this would have the same effect as this. The current here, given the same voltage, the current here will be the same as the current here, given the same voltage, because they're going to have the same total resistance in both places. So when they talk about that concept of an equivalent resistance, what is the equivalent resistance of these three resistors, right? Even though we could say total resistance, but when I talk parallel, it's not really total. So I'm going to use equivalent resistance when I'm talking about these resistors, and these three are the same as this. Right, so this circuit will have this basically the same general properties, having to use the same amount of voltage across 110 ohms as I did here across these 110 ohms. Okay, so there's the first one. The second one says if I have an 8, 6, and 48 in parallel. I may just finish with this question and then jump into today's stuff. Okay, so here's my source. I've got three resistors in parallel. There's 1, 2, 3, and sorry, they were 8, 6, and 48. R1, R2, and R3. Okay, so to find the total resistance from these three, so I'm going to use that 1 over x button on my calculator again. So 8, 1 over, plus 6, 1 over, plus 48, 1 over will give me an answer. I'm getting 0.31. I'm going to double check my math because I don't want to make any mistakes here. It's a lot of plus 6 plus 48, 1 over, equals 0.31. So now my 1 over RT equals 0.31. I'm going to take my RT up, my 0.31 down. So RT is equal to 1 over the number. It's on my calculator already. So I'm just going to hit 1 over X. I'm getting 3.2 ohms. Again, notice the same thing that I just said in the last question. The total resistance in this series is lower than the lowest one, 8, 6, and 48, but the total resistance in the circuit is only 3.2, right? Because this is the easiest one to get through. Those ones are harder. Even though they're harder, they still give the electrons options, which makes life a little bit easier for everybody, right? So the total resistance will always be lower for parallel than the lowest resistance there. Now, what that means is I can take this same circuit and if I replaced these three parallel ones with a series circuit for this voltage, I would get the same current. In both cases, V and I would be the same because this is equivalent to this. Okay. Really important concept, right? These three are equivalent to the 3.2 ohm resistor. Okay, so let's look at C. And then I'm going to move on to, there's a, oops, shoot. Okay, so B says I've got a 4.9 and a 9 in parallel in series with a combination of 4 and 12, which are connected in parallel with each other. Okay, so this question here is kind of a launch point for today's work. Okay, so I've got a 4 and a 9 in parallel, so sometimes it's hard to draw these. Here's my source, and I'm going to draw 1, 2 in parallel, okay, and that's in series with 2 more that are in parallel. Okay, so I've got 4 resistors, and I'm going to number them R1, 2, 3, 4, which are 4 and 9. R1 is 4 ohms. R2 is 9 ohms. R3 is 4 ohms. And R4 is 12 ohms. That's probably the hardest part of the question. Oh, I'm sorry, you can't even see what I'm doing. Okay, so let's just, I've got 2 resistors in parallel, 4 and 9. I've got 4 and a 12 in parallel, and this parallel set is in series with this parallel set here. Okay, so again, back to my camera. Okay, so there's my circuit there. I have 2 that are in parallel. I have 2 more that are in parallel. and I have two more, and then this parallel set is in series. In other words, electrons have to go through this set, and they have to go through this set. So that's how come these two parallel lines are in series. Now, what I have to do before anything is figure out how am I going to figure out RT, right? What is the total resistance? So because I've got two things in series, I have to add up the resistance I have here plus the resistance I have here. Right? But I don't know what the resistance is here, but I do know that I can find the equivalent resistance of these two by using my 1 over RT formula. And that will tell me what the equivalent resistance is, and then I can pretend that there's a resistor here with that resistance. I haven't left myself a lot of working room here. But if I say, what is the resistance of 1 and 2? It's equal to 1 over R1 plus 1 over R2. Okay? And if it's equal to 1 over 4 plus 1 over 9. So my resistance for 1 and 2 is going to be equal to, again, I'm just going to do my 1 over X button, plus 9. I'm getting 2.8 ohms. I'm going to leave an extra sig dig in here for now. Again, notice that my total resistance here is less than the lower one, which was 4 ohms. We do the same thing down here. My R3-4 parallel resistors could be replaced if I know what the equivalent resistance is here. So I'm going to say 1 over R3-4 equals 1 over R3 plus 1 over R4, right, which is equal to 1 over 4 plus 1 over 12. So my R3-4 resistance is 3.0 ohms. Okay, so I know that this provides 3 ohms of resistance. That provides 2.8 ohms of resistance. So together, if I want to find the total resistance from all, which is the ones from 1, 2, 3, 4, or just RT, it's going to be the 1, 2 resistance. How much is up there? Plus my 3, 4 resistance, which is 2.8 plus 3. And really it should just be 6 ohms because I've got 1 sig dig all the way through there. All right, so let me pull that out of the way. All right, so that is really the essence of what we're doing today. It's looking at combinations of series and parallel circuits. And the trick is really to look at how to attack the question, which is why they call it in the book the circuit analysis game, because you have to have a strategy, right, first for analyzing these things. Okay, so there's question 31C from last night. All right, so I'm going to go back to I'm going to go back to this circuit right here. This is similar to the one we just did, maybe even a little bit easier than the one we just did. Make that a little bit bigger for you. Okay, so notice that I have my four resistors, sorry, R1, R2, R3, and R4, right? And R1 is 5 ohms, R2 is 10 ohms, 15 ohms, and 20 ohms, right? So those are my 4 resistors, right? The question is asking me, a number of things. It is asking me what is the current going through each of these resistors. There's the first thing. The second thing, it's saying how much of the 120 volts gets used at each of these 4 resistors. In other words, what is I1, I2, I3, and I4, the current going through each resistor? And what is V1, V2, V3, and V4? What is the potential drop of the electrons at each resistor? Now, that being said, I'm looking at the fact that I have this, which is in series with this thing, which is in series with this thing. If I can figure out what the equivalent resistance is right here, then I can actually go forward and figure out what my total resistance is in the circuit. Okay, so let's start with that, because that's, given the resistances we have, that's our starting point. Okay, so let's very quickly, I'm going to draw a quick circuit here. You can notice that these don't need to be pretty. Mine aren't. Right? They just need to be able to give you the information to direct you through your question. Okay, so I've got my 120 volts power supply right here. That's V0, or starting voltage. And then I have an I0 or I total coming off the source. And then I'm going to go through my first resistor, come down and go through either this resistor or that resistor, and then through this resistor, R4. So those are my 4 resistors. Okay, and we're told that they are 5, 10, 15, and 20. 5 ohms, 10 ohms, 15 ohms, 20 ohms. Okay, and like I said, the question is, what is I1, I2, I3, I4? What is V1, V2, V3, V4? Okay, so to solve them, the only thing that I can do right now is look at the resistances and see if I can figure out what the total resistance is in the circuit. Okay, so let's start there. So if I know R2 and R3 are in parallel, I can figure out what the equivalent resistance is for those two. So R1 over R2, 3 equals 1 over R2 plus 1 over R3, 1 over 10 plus 1 over 15, and R2, 3 turns out to be 6 exactly. Again, notice that the total resistance here is less than the lowest one. Okay, if I'm getting an answer which is 75 here, I know that I've messed something up. If I get an answer of 13, I know I've messed something up. It's got to be less than 10. So now I know that I could replace this with a 6 ohm resistor. And if that's the case, I now have 3 series resistors, 5, 6, and 20. So I can find my total resistance. Right, total resistance is R1 plus R23 plus R4, which is 6, 5 plus 6 plus 20. So the total resistance in this circuit is 31 ohms. 31 ohms. Now that I know that much, I'm going to use all this information still because, again, remember, I know that this is 6 ohms of resistance. So if I know the starting voltage and I know the total resistance in my circuit, I could replace all of these with 131 ohm resistor, right? And I can calculate my I, right? So my starting current is my starting voltage divided by the total resistance in the circuit, which is 120 volts divided by 31 ohms. I'm getting a current of 3 point, I'm going to leave 2 decimal places here because 3.87 amps. Okay, so what is that telling me? It's saying when the electrons leave the source here with their 120 volts, I know that they're going to encounter 31 ohms of resistance, and this will be their speed, 3.9 amps. I know that if I replace this with a 6 ohm resistor, that the speed going through here will be 3.9 amps. Okay. When it gets to here, some of the 3.9 is going to go this way, and some of the 3.9 is going to go this way, but they will come back together as 3.9 and travel this way. So this I0 is also the same as I1, because I know that that's the speed that it goes through the first resistor. It's not going to be the same as I2 and I3 because they get divided up, but it will be the same as I4 because they're going to come together at the end here. Right, so those are my I1s and I4. Okay. Now that I know the current going through this resistor, I can find the voltage of this resistor. Right, so V1 equals I1 R1, which is I1 we know is 3.87 amps times R1, which is 5 ohms, and I'm getting 19.4 volts. If I want to figure out R4, because I know, so if I want to find V4, because I know I4 and R4, right, there's my I4 that I've already calculated. V4 is going to be I4, R4, right, which is going to be my 3.87 times the resistance of 20. In other words, I'm going to take the answer that I had before. I'm getting 77.4 ohms, volts. Okay, so think about it for a minute now. Electrons are leaving here with 120. They're going to spend 19 of their 120 here. They're going to spend 77 of their 120 here. Now, if they've come this way, so 19 and 77, that's 86, that's 96.8 volts. But they had 120. So what that means is we're still missing 23.2 volts. 120 minus 96.8, which is 23.2 volts. So 23.2 volts. How does that work? Well, if they come this way, they'll use their 23.2 there on their way back so that they can use all 120. If they go this way, they will also use 23.2 volts on their way back because I know they've used 19 and 77, and if they've gone either way, they're going to use the other 23.2 volts. So that 23.2 volts is my V2 and my V3. Right? Because that's the amount of voltage that the electrons had to use that they were given. Because remember, they were given 120 and they have to have 0 by the time they get back around the rest of the circuit. Now if I know, so I know V1, V2, V1 I know, V2, V4 I know, V2 I know, V3 I know. Right? I also know I1 and I4. I'm missing 2 pieces. I'm missing I2 and I3. Well, I2 equals V2 over R2. Right? My V2 is 23.2 volts divided by R2, which is 10 ohms. And my I3 equals, V3 over R3, which is 23.2, right? My V3 I know is 23.2, divided by my R3, which is 15 ohms. Right? I'm getting 1.55 amps. Sorry, that should be amps up there. So if I add these two currents up, 2.32 and 1.55, I'm getting 3.87 amps. Not that I needed to do that, but I'm just using that as a double check. Okay, so what do I know? I know electrons leave here, I0 at 3.87 amps. They travel through here at 3.87. They get to here, 2.32 go this way, 1.55 go this way. They have to add up to the 3.87, Kirchhoff's current law, right? The sum of the currents out of a junction have to equal the current coming into the junction. The 2.32 and 1.55 will get here together, and they have to add up again to make my 3.87, and they come back along here and they're done. So I now know all my currents and all my voltages. Right, there is my currents. Those are two of the voltages. These are two more, the voltages, and these are my missing two currents. So I know I1, I2, I3, I4, V1, V2, V3, V4. This takes a little bit of practice. Once you've done them, there's no tricks to them. There's no tricks to them. So be always thinking that the current is going to, in a series, remain unchanged. In a parallel system, the current will be split. In a parallel system, the voltages are the same for both. If they have to spend that missing, whatever it was, 23.2 volts, this way or this way, it doesn't matter. The voltage 2 will be the same as voltage 3. Even though the current has been dropped by half, or into smaller amounts, they're using the same amount of voltage. And then the voltages, the current will be the same here as here, but again, the voltage will be different because the resistances are different. So we're using all the tools that we have at this point to solve these complex circuits. Now you really want to give yourself an entire page, right, to do this. It took me an entire whiteboard, and even at that, it's really crammed in there. Tons of math, but hopefully the logic makes sense to you there. All right, so in the textbook, they've actually gone through and they've done the scorecard, right, which is what they call it. So we were given R1, R2, R3, and R4 resistors, right? There were the resistances, 5, 10, 15, and 20. We calculated the missing voltages and we calculated the currents all the way along. Again, notice that they've kept some extra. You say, well, there's only one sig dig here. How come I'm having 3 sig digs in all these answers? I would tend, just for the, I don't know, just to make sure that the math adds up. If you do too much rounding, these things get a little bit wonky. So I would leave some extra decimal places or extra sig digs in your answers as you're working through them. Now, further down here, so they walk you through the step, right, through the steps. So you can actually follow through if you want. They've done exactly what I've just done, but they walk you through all the different calculations. Now, they give you some other ideas as to what you could do, right? And again, there's different ways to solve this. Right. It's a bit smaller. Yikes, that should be giving you nightmares. That's not a very nice graphic. Original circuit. Again, if you've got combination of series, if they're all series, then you basically are just going to add them up. If they're all in parallel, you're going to do your 1 over RT thing. If you've got a combination, boy, I really hate this graphic. You're going to have to basically use the combinations of these formulas to make it all work. All right, so a bit further down, I'm gonna come back and do this power note tomorrow and the cost of electricity tomorrow. So in the textbook, they've given you a series of, pardon the pun, of questions. So I've got one here where I've got, this is question 35. So all of this is question 35 from A to F. Okay, so if I look at A, I've got 3 resistors in parallel. This time they've given me the current, but not the voltage. But if I know I1, then I know I2, and I also know I3. If I know how much voltage was used here and how much voltage was used down here, I think. No, I don't even know that, right? Oh, but I do know the amount of resistance here, right? So you're going to have to navigate your way through the pieces of information. So I'm going to do a couple of more samples just to get our heads around doing these things. Okay, so here's one here. Okay, so it says, let's make this a bit bigger. Okay, I'm not sure what device you're using, so make sure you can see what this is all about. Okay, so I'm given R1 up here, which is 15 ohms, R2 is 25 ohms, R3 is 35 ohms, and it's asking what is the current at the source, I0, what is I1, I2, and I3, what is RT, and what is V1, V2, V3. Okay, so if I can move this down just a bit, oh I can, okay. So there's our circuit, so you can see the 3 resistors. So let's work through this one step by step, and then maybe we'll work on a couple of the other ones that you're not just given resistances, you might be given currents and voltages like the ones that we just saw there a moment ago in our textbook. I might even post this page, this PDF for you to have as a resource if you want to do more practice and see how, because they walk you through the solution again. So I'm seeing oops. Uh, 15, 25, 35. Okay, so there's R1, R2, and R3, and we must have been given a starting voltage . 12 volts. Okay, so I'm going to start, I'm given resistances, so I'm going to try and calculate RT. So if I know RT, I can find the current coming out of here, and then we can kind of work from there. All right, so I've got 2 resistors in parallel, so I can find my equivalence to 2 and 3 by using 1 over R2 plus 1 over R3, and I get the equivalent resistance to R2, R3. Oops, that's not going to work. 25, 1 over, plus 35, 1 over equals, and 1 over 14.6 ohms. Okay, notice how fast and easy that X, 1 over X button makes it for you. 25, 1 over, plus 35, 1 over equals, and 1 over 14.6 ohms. So I now know electrons are going to leave here, they're going to have 15 ohms, and then another 14.6 ohms here. So I know now the total resistance in the circuit. R1 is in series with R2, 3. Total Total resistance is 29.6 ohms. Now I know my resistance total for the circuit, and I know the voltage total. I can find my current total. I'm getting 0.41 amps. Okay, so that's the speed that they leave here at. Oh, but that must be the speed they go through there at, because the speed through a series is constant. So there's my first current. Now, if I know my first current, I can also figure out my first voltage. V1 equals I1 R1. I know I1 is 0.41. I know R1 is 15 ohms. I'm getting 6.1 volts. So electrons leave here with 12, they dump 6.1 here. So they now get to here, they have 5.9 left. Right, 12 minus 6.1. They've used 6.1 of their 12, they have 5.9 left. So R2 is going to be the other 5.9, or R3 will use the other 5.9. So V2 is going to be the same as V3, which is equal to 12 minus 6.1. So I now know V1, V2, and V3. And if I know, and I know I1, I now have to calculate I2 and I3. So I2 equals V2 over R2. I know V2 is 5.9 divided by my 25 ohms. And my I3 is equal to V3 over R3, which is 5.9 volts divided by 35 ohms. 0.24 amps here. I'm guessing this one should be 0.41 minus 0.24. This should be 0.17. But let's just double check. 5.9 divided by 30. I'm getting 0.17 amps. Right, so I know I2, I3, and I1. And I know V1, V2, and V3, and RT, and I0, right? So those are all the things that it was asking us to calculate in the question. Right, so there's a sample, another sample, okay? And then it says, what if they give you other information? So let's look at one more, and then I'm going to stop and leave you some time to try these. And hopefully, you're okay with this. It really looks ugly because there's a lot of math, but it's V equals IR, V equals IR, V equals IR, V equals IR. Right, it's all Ohm's law, right? Because in the circuit, I have a V equals IR. In every resistor, I have a V equals IR. Right, so, and then I've got series things, RT equals R1 plus R2 plus R3 plus R4. I've got my parallel resistors, 1 over resistance total equals 1 over the resistances added up. Right, so there's not a lot here. You've really got to have your head on when you're doing these things. Right, you got to be clear. And it just comes with practice. It just comes with practice. Okay, so let's look at oops, wrong one. Let's look at this one here. Okay, so this one is a little more complicated. They've added an extra resistor. Okay, so just look at the resistor for a minute, start thinking about your strategy. So I see a number of things. I see in that top parallel line 2 resistors that are in series, R2 and R3. I've got an R4 below that, which is parallel to the 2-3 line. And then if I could replace R2, 3, 4, which are parallel resistors, with a single equivalence, I could add R1 to the R2, 3, 4. Okay, so there's kind of my logic in setting this up. Okay, so I'm going to draw it first, because I find if I can't see it, then obviously can't do it. So let's R1, R2, R3, R4. So I've got an initial power supply. I have R1, I have R2, R3, and R4. Okay, so what information are we given in this question? Okay, so this is very, very different here, right, than the last question. So in this time, we're given the V at the source, which is 12 volts. We're given current 1. So I'm going to put these on as I'm rebuilding the question. Current 1 is 0.5 amps. V3 is 2.5 volts. So this is R1, this was R2, R3, R4. We're told V3 is 0.25 volts, and we're told V4, sorry, it was 2.5 volts, I think. 2.5 volts, and V4 is 5 volts. Wish I could split my screen so you can see the question as I'm working through it, but I can't do that on my laptop here. So I've got 2.5 volts here, 5 volts there. Are we given any more information in our question? R3 is 10 ohms. Okay, so that's it. Starting source, 1 of the currents, 2 of the voltages, and R3, which is 10 ohms. Now I really crammed this in here because I want to give myself lots of room to work. All right, so what can I do? I don't know any resistances except 1. I don't know any voltages except 1, 2. So where do you start? Well, I see I've got a resistance and a voltage here. I have a voltage here too. So I know that when the electrons leave here with 12 volts, they're going to spend some here and maybe go this way and spend 5, or go this way and spend 5. Because if they've spent some up here, I know V1 right off the top. Right? If I have started with 12 and I used 5 here, I had to have used 7 here before I can move through. I also know that if I had 5 going through here and I used 2.5 at R3, I know that R2 is also 2.5 volts. Right? And now if I know what R2 and R3 are combined it's at 5 volts. So I've got lots of information here now. So I know V1, I know I1. I could actually go ahead and calculate R1, which I didn't do before. Let's do R1 right now. V1 over I1, which was V1 was 7 volts, divided by my current, which was 0.50 amps. Okay, so I know my R1 is 14 ohms. I know R2 and R3 now are 5. I know R4 is 5. So I can say 1 over all of those resistors, 2, 3, and 4, is equal to 1 over the resistance in the 2, 3 line plus 1 over the resistance in the 4 line. In other words, 1 over 5 plus 1 over 5, right, which is... So I'm going to do all my 1 over 5 plus 1 over 5, and then 1 over that number gives me a total resistance of 2.5 ohms. Again, remember if I've got 5 R2 and 3. Sorry. Let's go back here. I'm kind of rushing through this. So I know I1, so this was 5 volts. So this is 7 volts. So this is 14 ohms. I know R2 and R3. I know V4 was 5 volts, and I know V3 is 2.5 volts. So I know this should be V2. Sorry, there's my mistake. V2 is also 2.5 volts. Now, let me fix this because I think I put a V instead of an R. Okay, so I have my voltages. Again, if I have more room, I'd like to put these right on here. I know that this is 2.5 volts. Okay. I know it's 5 volts. I know that's 10 ohms. So that's 10 ohms, and that's 2.5 volts. I can calculate the current here. And I also know that if I know the current going through this resistor, I also know the current going through this resistor because they're in series. So I can find I3 equals V3 over R3. I'm sorry about that. I3 is going to be equal to 2.5 volts divided by 10 ohms, 0.25 amps, which is going to be the same as I2, right, which is going to be 0.25 amps, because whatever speed I go through this one at, I had to be going the same speed at here. And now, if I want to find the speed going through my resistor 4, again, there's several ways to do this. What if I find the total resistance of R2, R3, and R4? But I can't do that. 5 ohms, 0.5. Oh, if I know the current going this way is 0.25 amps, and it was 0.5 coming to here, 0.25 amps had to go through this way. So I4 is going to be my 0.5 that got to the junction, minus the 0.25 that went through the top line. So my I4 is now going to be 0.25 amps also. So now that I know I'm missing one piece, which I think, I'm missing 2 pieces. I'm missing R4 and I'm missing I've got I0 already. So to find R4, it's going to be V4 over I4, which is 5 volts divided by my current of 0.25, which is 20 ohms. So I now know my missing R2 is going to be equal to V2 over I2. V2 is 2.5 volts divided by my I2, which I know is 0.25 amps. Okay, so you can see a little bit of kind of jumping around a little bit, but basically just using V equals IR, V equals IR, V equals IR, V equals IR, right? It doesn't tell me what the total resistance is in the circuit, but if I know for the whole circuit, I need to find the equivalent resistance. So if I know what R2, R3 is, so let's do that. 1 over R23 equals 1 over R2 plus 1 over that. R2, R3 is equal to R2 plus R3. Ugh. R2 was 10 ohms. R3 was 10 ohms. So I've got a total resistance of 20. Now if I want to find the equivalent resistance of 234, 1 over the resistance of 234 is equal to 1 over the resistance in the 2,3 line plus 1 over the resistance in the 4 line. Right? And if I do all the math, I put my R23 was 20, R4 is 20, right? So I end up with, and I can solve from my R234. I'm getting a total resistance of 10 ohms. Again, just double check. I've got 20 here and 20 up there, so my total resistance, equivalent resistance, has to be less than the lower, which it is. And now I can calculate my RT. Final number here is the R1 plus the resistance of the 234 equivalents. R1 was 14 ohms up there. Plus 234 is 10, which is 24 ohms. Now, I could also find RT if I know V0 and I0, but I do know V0 and I0, right? So RT would be V0 over I0. 12 divided by I0, which was 0.5 amps. And I get 24 ohms that way too. So there's two ways to get, again, it's probably lots of ways to work through these circuits. There's no right or wrong way, but there is only one set of correct answers, however you get to it. Okay, so like I said, ultimately, the trick here is to just practice a bunch of them. Hopefully you've done the series ones first and the parallel ones first, and then you can go ahead and jump into these complex ones. So I'm going to stop there. I've got another document here that I'll post. This gives you practice with just series and parallel resistors. Again, this is 11.8. So I'll post this. There is a sample problem there and a couple of practice questions. For parallel resistors, again, there's a sample problem and a couple of practice questions. Then there's another parallel tutorial there, right? And then there's some practice. I'd almost recommend just doing these ones up here because they've actually given you all the answers. Whoops, they've given you all the answers for the practice questions after tutorials 1, 2, and 3. And then once you finish 11.8 here on series and parallel circuits, then jump into 11.9, which is circuit analysis using mixed circuits. And again, they've done the same two for you that I just did, right? That one there that we did a moment ago. They've given you strategies and a plan and a way to attack it. Again, sometimes it's easier to see someone do it. Sometimes you just want to read through it and get your head around what they're doing. All right, so I will post those two in a few minutes, and hopefully you take the time to run through these videos. This stuff is huge, right? But it's not difficult. It's a little tricky, but you just got to get your head. Again, I don't have much room on my one whiteboard here. If I had more room, I'd like to build my answers around the circuit like they've done here, right? I can show how, I don't think I like showing that it starts with 12 and goes down to 5, and then the 5 goes down to 2.5, and the 2.5 goes down to 0. I think that's a bit redundant. I think you just need to know that it loses 7 here, loses 2.5 here, loses 2.5 here, right? It would lose 5 volts down here, right? I find that more useful than showing all the individual voltages at each point, because we don't measure voltages at each point. All right, but again, there's some practice and all the answers are given there. All right, so hopefully I haven't scared you off. So that's 16.7. Some people really like doing this stuff. It's almost like doing a jigsaw puzzle. And some people just think this is just too much. But once you've done some, you can realize it's just V equals IR a million times over. And then series and parallel circuits. So I'm going to do this note tomorrow. Again, notice I've got a live class planned for Friday. I think I'm going to probably still do that. If we need more help between now and then for these complex circuits, let me know. I can always come back on and just let me know, and I can either do another video with a couple more questions. I find them a little bit easier to do maybe on the whiteboard than on the iPad, but whichever is easier. And then again, just getting ready for our final electricity and magnetism test here next week on Wednesday. And so we're almost there. Almost there. I've been marking the assignments. Some of you have handed in a bunch of assignments, and I was just marking them last night. And that's awesome that a number of you are actually getting caught up with some of the missing things. Again, just keep getting them done. I know this is a crazy busy time, but just try and get everything done. Even if after that final test, if you've got 1 or 2 assignments still to do, or 3, whatever, you can still do them. I will take stuff up until the end, generate a mark for everybody here on the 24th, but I will update them if you hand more stuff in after that. So probably by the time I go to bed here next Wednesday night, I should have your final marks, unless you've got other things that you're going to add in. All right, so I will leave you with that. I will post those 2 documents. I'm going to call them series and parallel circuits and complex circuits in Mr. Senna's notes and assignments. All right, so take care, everybody, and I will be talking to you soon.